Hello, my name is Daniel Große from the Johannes Kepler University Linz in Austria, and I'm doing this tutorial together with Vladimir Herd from the University of Bremen and DFKI Bremen and Eike Jentsch from Minres Technologies. Our tutorial is about cross-level compliance testing and verification for RISC-V. So here's the agenda of our tutorial. First, I start with a background on RISC-V, and then we have separated our tutorial in two parts, where the first part is on compliance testing and the second part is on cross-level verification. So what is RISC-V? It's a royalty-free, open source, ISA, this means instruction set architecture. It's highly modular and extensible, and there's a rapidly growing ecosystem, and it's very popular in academia and industry. So RISC-V is not a processor. In fact, it is an instruction set architecture. This means it defines the interface between the hardware and the software. And here on the right, you can see the different layers of abstraction, starting from the application, then algorithm, then programming language, assembly language, and machine code. And then you reach this instruction set architecture. And here are the instructions defined which the hardware understands. And then you go down the microarchitectures and so on and so forth. Now, the ISA in general defines the number and types of instructions, this means the encoding and semantics, the number and types of registers, the memory accessing modes and the addressing modes, and so on and so forth. Now, concretely for the RISC-V ISA, we have a mandatory integer instruction set, around 40 instructions, which is defined for 32, 64, and 128-bit. Moreover, we have optional extensions like multiply, atomic, single precision floating point, and double precision floating point, and so on and so forth. And for example, this RV32 IMAFD is an abbreviation, or can be abbreviated as RV32G. And then based on this, of course, RISC-V also defines the control and status registers, so ways how environment interaction can be done, as well as privilege levels like well-known machine supervisor and user modes. So why is RISC-V so successful? On this slide, you see the logos of the member companies of the RISC-V Foundation, and they all work together to innovate and to drive the RISC-V standard forward. And today there are more than 580 members, and of course there are recent press releases, like for example this one, like Intel be aware of the upcoming open source business based on RISC-V, or the very prominent one is Western Digital, which uses RISC-V in their controllers for their storage systems. And moreover, for example, the Google Open Titan project, which aims to build a silicon root of trust. So let's come to the first part of this tutorial, which is on compliance testing. So what is compliance testing? With compliance testing, you want to show that a processor core, this means a concrete implementation, or for example an instruction set simulator, adheres to the ISA specification. So compliance testing is not formal verification or verification. Instead, you perform compliance checks or tests, and there you check, for example, the available registers, their width, the access combinations, the correct sign extension, and also you check that the configured instructions are available, and you run some basic sanity checks. For example, that the add performs an addition, and not a subtraction. Moreover, you check that no additional behavior accidentally has been added. And all this now ensures compliance in the sense of that the compatibility with the RISC-V software ecosystem can be ensured. So what is the challenge of RISC-V compliance? So Alan Baum, the chair of the RISC-V compliance task group, said in an interview, RISC-V is an open source standard ISA with exceptional modularity and extensibility. Anyone can build an implementation and there are no license fees. Implementers are free to add custom extensions to boost capabilities and performance, while at the same time don't have to include features that aren't needed. So, an increasing large number of customized RISC-V cores is being implemented. An unconstrained flexibility greatly increases the risk of introducing incompatibilities. And hence compliance testing becomes very important and challenging. So on this slide, I want to provide an overview on two RISC-V compliance testing approaches which we have developed. The first one is a specification-based test suite generation approach, which we denote as positive testing. And we show that we are able to increase the coverage significantly. And this one has been published at date this year. And the second approach, which complements the first one, uses a fuzzer for test suite generation, and we denote it as negative testing, since this approach allows to consider illegal instructions to also ensure that no additional or unexpected behavior has been added. And here we could show that we found bugs and mismatches in several RISC-V simulator, including the official reference simulator. And this work has been published at DEC this year. So how does RISC-V compliance testing work in general, and where are the problems and challenges? So first of all, it's not clear how to best approach this compliance testing problem. And the current official solution is as follows. Essentially, there are separate compliance test suites per extension configuration, so per RISC-V ISA part defined. And this looks as follows. So the compliance testing is based on a manually test suite generation approach. This means a test suite is coded, and this test suite has to be run only once on a reference simulator, and then per test case of the test suite, a reference output is generated. Now you use this compliance test suite and run it on the core or simulator under test, and then you just have to check against the reference outputs to see whether the core or simulator is compliant. So obviously the problem here is that it's a significant manual effort for creating all these tests, and it's very difficult to get high coverage. So what is our contribution? We will show this later for an RV32i in a case study, and so we have very clever and nice means to specify the test suite, and then we use formal techniques, in our case an SMT solver, as underlying engine for a generator. And then in our approach we have basically two sets of constraints. One set contains the instruction constraints, so denoted here as A, And the other set are the coverage requirements, where we also formulate constraints, which are then used in the generator. And here we distinguish between structural as well as functional coverage requirements. Now this all allows us to generate respective compliance test suites. And of course, for this you have to provide some basic data of your target ISA, which we call metadata. For example, the registers, the CSRs, and the instructions have to be known. Now here's a high-level overview how our approach works. So you see here on this slide, in our specification format, the coverage requirement constraints which are processed one by one. And for example, we require here that there should exist an instruction where the opcode should be equivalent to add immediate. And then this one is ended up with all the possible instruction constraints. And then the finally generated logical formula is solved using an SMT solver. And then you get a solution as shown here on the right. For example, since we consider this coverage requirement constraint here currently, we get a solution which here has as opcode the add immediate, then the destination register X1, the source register 1 is X2, and we have an immediate value of 19. And our approach also can generate a preloaded value for the source registers. So out of this solution we can derive this add immediate instruction, obviously having these two registers and the immediate value. And then we use in general per instruction class, we have so-called code templates. Yeah, and in this case here, for this class of instructions, we have here some load immediate, for example, for this register, source register value, and we have, of course, for finally storing the output which is used for the signature computation, we have some code afterwards. So visually this template is used and now filled in with the solution here shown in this light blue, and then there of course is some general start code and some general end code, and now here at this label output begin is loaded into this register X3, and then the result of this to be tested generated operation is stored at this address. So you have now an idea how our generation approach works, and here are some experimental results. We created an RV32i specification file which has roughly 186 non-blank lines. And we generated now with our approach 8,900 test cases in roughly 400 seconds. And this allows us to increase the ISA coverage from 67 to 86% in comparison to the official compliance test suite. And okay, we use a modern computer for this, and the generator has been implemented in Python. And for constraint solving, we use this well-known set3 solver from Microsoft. So on this slide, the experimental evaluation is summarized in a table. So first of all, we have here these 4 different instruction classes, and here in this second part of the table you see the number of tests in the different classes. And as can be seen here, this is the official compliance test suite. Our automatic generation approach always generates more tests, and as already reported, we have overall nearly 9,000 tests. Now here on the right side, you get some information on the quality of this test suite. And here for coverage, measurement GRIFT is used, which is the Galois RISC-V ESA formal tools. And this GRIFT is employed to measure the instruction coverage of the official compliance test suite. And there you get absolute numbers. And here is the theoretical maximum number, which can be derived on this Haskell model. And basically what you get now with our approach is, if you now divide 384 by 446, you see that we have a coverage of 87% versus 67% resulting from the official compliance suite. Now, even if all these results are very good already, negative testing is not done at all until now. So why is negative testing very important? Because negative testing allows to ensure that no additional behavior has been accidentally added to the core you have implemented. Now, our second approach here uses now fuzzing for test generation. And fuzzing is very effective and has been initially used for security testing for software. And now we use it here for test generation. And it allows to get a broad coverage through very extensive randomization. And the important thing is that the test selection and the mutation is guided with coverage information in a coverage-guided fuzzer flow. So this is how our fuzzer-based compliance testing approach looks like. We use a fuzzer to generate our compliance test suite, and this is done in an automated and strong fashion with this goal of negative testing. So we have the fuzzer, we generate input, and these are now instructions to a simulator. And this simulator, of course, executes these instructions. During execution, we collect coverage, and this is reported to the fuzzer, which collects a coverage database. And whenever new coverage is resulted or collected, then we increase or put these new identified input and collect them in this set of instructions. Furthermore, we need a test template, which is assembly. Of course, has to be compiled down and preloaded in the simulator. And these final input here and the template are combined to form the compliance test suite. Now, to realize this complete loop, we leverage the LLVM-based libfuzzer library. And to further improve this approach, we have defined custom mutators as well as custom coverage. Moreover, we filter out here several instructions, and this I detail in the following. So why do we need to filter out certain instructions? The compliance tests are written in a platform-independent assembly. And of course, the memory layout is defined by platform-dependent macros. Thus, we cannot use hard-coded memory or jump addresses. And that's why we have this filter component, which drops invalid tests. So this means, for example, unsupported instructions like wait for interrupt, CSR, MRET, or infinite loops, or hard-coded jumps or memory accesses. And we do this using a static analysis, which is conservative, and all illegal instructions are kept. And of course, their semantic is clearly specified, and this overall allows to retain negative testing capability. On this slide, I want to briefly summarize the experiments we have performed. So we have used a modern computer, and here is some generation data using our approach. For example, we needed 30 minutes to generate our final test suite, and overall nearly 14,000 tests have been generated automatically. Here is a high-level table summarizing the results we obtained. So here in these different rows, you see 3 ISA configurations, and here in the columns you see different simulators. And these numbers here, they show the number of mismatches against RISC-V OVP sim. And note, this is the official reference simulator for RISC-V compliance testing. And mismatches now in the sense of that the signature values differ, and hence we saw a mismatch. So, and as can be seen here, for Grift we have even very large numbers, and essentially for all simulators we could report and find several mismatches. Now for sale, this formalization, we always observed a crash. So to summarize, we found bugs and mismatches in every considered RISC-V simulator. Of course, all the details and explanations can be found in the deck paper. This brings me already to the end of the first part of the tutorial, and I have presented a strong framework for RISC-V compliance testing. And this framework combines positive and negative testing. I have discussed first a specification-based test suite generation, which allows to increase the ISA coverage significantly. And this approach is complemented with a fuzzing-based approach to focus on generation and testing of illegal instruction. And here we were able to find bugs and mismatches in several RISC-V simulators, including the official reference simulator. Finally, even if all these techniques are strong, please recall thorough design verification is still necessary. So now I hand over to Vladimir for the second part of this tutorial.
Everybody from my side as well. I'm Vladimir Hert from the DFKI and University of Bremen, and I will present the second part of our tutorial. In particular, I will talk about our cross-level approach for processor verification in the RISC-V context. I want to start with a brief high-level overview on what we have done. This includes two main points. First, we developed an efficient approach for processor verification, and second, we have found and fixed several serious bugs in an industrial pipeline RISC-V processor. In particular, the processor is from the Good Folks series, or TGF series in short, from Minres. This core also is used as ecosystem core in the BMBF-funded Scale for Edge project. In the following, I will start with a motivation and general overview on processor verification, Then I will talk about RISC-V verification approaches. Next, I will outline our contribution to improve verification, and finally show and discuss experimental results. When you think about processor verification or verification in general, there are basically two different ways how to approach the problem that have certain advantages and disadvantages. On one side, we have formal verification. Formal verification is conceptually the best way to address the problem because it enables to obtain a proof of correctness by being complete, which is a major advantage. So formal verification methods can prove the correctness of the design, but they may have limitations as well. Two main points are here. First, the complexity of the algorithms and setup involved to use formal verification. And second, potential scalability issues, which can lead to the point that formal methods are not applicable to obtain a complete proof. Therefore, simulation-based methods are still very important. In contrast to formal methods, they essentially rely on randomized testing. That means they basically try to guess good inputs and track coverage information to measure the verification progress. Therefore, simulation-based methods are inherently incomplete, as they do only consider parts of the input space. However, at the same time, they are not susceptible to scalability issues and are rather easy to set up and use. Thus, we have a trade-off between formal methods and simulation-based methods. For the aforementioned reasons, simulation-based methods are still widely in use today for verification purposes to complement and cross-validate formal methods. In this work, we focus on improving simulation-based methods for processor verification in the context of RISC-V. On this slide, I want to talk about the Google RISC-V design verification, or in short DV, approach for RISC-V processor verification. It is based on generating test cases and conceptually is representative for other RISC-V verification approaches as well. Starting on the left side, you can see the instruction stream generator, or in short ISG. The ISG generates test cases, one after another. It is based on constrained random generation using UVM and System Verilog. The test cases are available in source code format, typically assembler. As I said before, they are generated one after another. Each test case is passed to a compiler to obtain an executable binary file. The binary file is then loaded on the RTL simulator that simulates the RTL description of the processor under test, and the reference instruction set simulator, or in short ISS. Both simulations produce log files which are then analyzed for mismatches, which indicate a bug in the processor under test. And as I said before, such a test generation approach is used by other RISC-V verification approaches as well, not just Google's RISC-V DV. Now, when you look more closely at such a test generation approach, a few problems become visible that can be improved to make the verification approach even better. In the following, I want to discuss these problems. The first problem is that the generated instruction stream needs to be restricted to avoid infinite loops. The reason is that an infinite loop will cause non-termination of the test simulations and thus is not supported. To deal with this issue, typically a conservative approach is used to restrict control flow. For example, a strong conservative requirement would be to avoid backward jumps altogether. In addition, infinite loops can also happen due to trap loops. Illegal instructions or load store operations that access unmapped memory ranges will cause a trap and thus perform a jump to the trap handler. This in turn can cause an infinite trap loop. Again, typically conservative rules are applied to avoid trap loops. A second problem are periodic restarts. Each test case is considered separately and causes a reset of the simulator state. This means it is executed from the initial state again. However, long test sequences may be very important to find intricate bugs. A third problem are performance limitations. When you think again about the test generation approach, each test case involves several steps with inter-process communication. First, the test case is generated and written to a file. Then it is compiled into a binary, and next it is loaded on both simulators, and log files are produced and finally compared. These inter-process communications can cause significant performance overheads. And finally, RISC-V is designed in a very modular way with significant configuration options. In particular, for the privileged architecture, which includes the CSRs, the specification offers a lot of implementation freedom. It is possible to implement two CSRs differently and yet to be compliant with the specification. Now, when you have a generic test generation approach, it tends to avoid instruction streams that touch on such implementation freedom behavior, because it can cause spurious mismatches in the testing process. Thus, the test generation process again is restricted. To address these problems, we propose to use a single, endless, and dynamically evolving instruction stream in a tight co-simulation. So the actual problem is still the same. We have an RTL core under test and a reference ISS to compare the results. In the following, I will present our solutions to address the aforementioned problems one by one, starting from the back. So we basically modify the ISS to exactly match the RTL core behavior to be able to generate arbitrary instruction sequences with respect to CSRs. To address the performance issue, we place both models together with the instruction stream generator in a single application without using any inter-process communication. The ISG writes the complete test case directly in binary format into the memory of the RTL core under test and the reference ISS. They both run in a tight co-simulation, and we compare the architectural state after each instruction. We address the first two problems by generating one single, endless, and dynamically evolving instruction stream at runtime. The idea is to return a new instruction every time the RTL core performs a fetch operation. By doing so, infinite control flow loops do not cause any problems because they are resolved very quickly. In addition, there are no restarts involved because the instruction stream is endless and continuously evolved. The same instruction stream that is fetched by the RT fed into the ISS for execution. While this conceptually seems rather straightforward, the main problem is how to feed the same instruction sequences that goes to the RTL core into the ISS. This is actually the main challenge involved here. The key problem is that the fetch behavior between the RTL core and ISS is different. So the RTL core fetches instructions in a different way compared to the ISS. For example, because the RTL core has a pipeline, and potentially other optimizations such a prefetch buffer. The pipeline causes the RTL core to prefetch instructions before the previous ones have completed. Now let's take a look at an example to illustrate the basic problems. You can see a fetch sequence on the left side from the RTL core. 5 instructions are shown together with the program counter. They are fetched from right to the left. So the RTL core starts by fetching program counter 0 and an add instruction is returned. Then it fetches a jump instruction at program counter 4. The jump goes back to program counter 0. However, the RTL core prefetches 2 sub-instructions before fetching the 0 program counter again. Thus, the RTL core executes 3 instructions in total: add, jump, and XOR. As you can see, it is not possible to directly pass the fetched instructions to the ISS. It also does not work to search the fetched instruction stream using the ISS program counter because the same program counter can appear multiple times in the fetch stream. This instruction matching problem is the main challenge in applying our methodology. Essentially, we address it by extracting the completed instructions on the RTL core and using them in combination with the ISS fetch program counter to search for a match on the instruction stream. However, instructing the completed instructions from the RTL core requires a deep pipeline understanding. You can find more details on the involved challenges and our solutions in our recent FTL paper titled Efficient Cross-Level Testing for Processor Verification, a RISC-V case study. In the following, I want to talk about the instruction stream generator. As I said before, the ISG is based on one endless instruction stream that evolves dynamically at runtime and thus supports arbitrary control flows. Therefore, the foundation of the ISG is a fully randomized instruction. Consider additional extensions on top of that to guide the test generation faster towards interesting cases for a more comprehensive testing process within a shorter time frame. In particular, a full randomization would favor illegal instructions too strongly, which is addressed by our generation rules. The first rule is to inject a random instruction opcode to create a valid instruction, but keep the instruction fields randomized. This rule is very simple, but at the same time very generic and effective. Also extremely important to ensure that a large set of legal instructions is considered, because as I said before, pure randomization tends to generate illegal instructions due to the significantly larger state space of illegal instructions. You can see an example on this slide, starting with the fully randomized 32-bit instruction as shown on the top. The @e opcode is injected, resulting in the randomized @e instruction shown at the bottom. So the immediate destination registers stay random, but the instruction becomes a valid @e instruction. The second modification of the randomized generation is to mutate the instruction fields based on a predefined rule. We provide a set of rules that reason about the structure and values of the instructions. The rules are derived based on the RISC-V instruction format. We provide rules to inject special values such as the min value, the max value, or -1, 0, and 1 into the respective immediate field. Other rules reason about the register structure. For example, mutate the destination register to 0, since the 0 register is hardwired in RISC-V and thus a special case, or mutate the destination and source registers to be equal. This example is shown on this slide. Starting with the previous randomized @e, as shown on the top here, we apply a mutation that changes RD to match RS1. Therefore, we obtain a special @e instruction as shown on the bottom. In addition to these extensions, we also consider generation of instruction sequences, and the sequence consists of a fixed number of instructions that are designed to perform a specific task and can be randomized. For example, 2 RISC-V instructions that in combination can load a large immediate value into a RISC-V register. Now I want to show you some more details on the overall design of our co-simulation test bench, where the RTL core as well as ISS and ISG are embedded. So we have the RTL core under test and reference ISS. The RTL core is packed inside an adapter which enables to access the RTL core data as well as extract the executed instructions. They both fetch from the same instruction stream, which is responsible to feed the same instructions to the RTL core and the ISS. The stream is populated by the ISG. The RTL core fetches first and gets a new instruction on each fetch. A test controller is provided to control and access the RTL core as well as the ISS. It compares the architectural state, in particular the register values. The program counter are compared implicitly by matching the instructions on the generated stream. CSRs are compared by reading them into the general purpose registers. We assume a Harvard architecture. with separate installer memories. The ISS and RTL data memories are initialized with the same random seed, and thus will return the same data when they are accessed. Next, I will present our experimental results. As a case study, we applied our approach for the verification of the pipeline 32-bit industrial RISC-V core from MinRes, in particular the TGF series core. The core has been implemented in Spinal HDL. It is designed to be highly configurable on the microarchitectural level, such as choosing the shifter implementation and pipeline levels. For this evaluation, we use the standard configuration. Spinal HDL provides an option to generate a Verilog description. By using the Verilator tool, we obtain a C++ RTL model from the Verilog code. Then we have integrated the C++ RSS of our open source RISC-V virtual prototype in a co-simulation with the RTL model. The test loop involves two steps that are continuously repeated. The test bench is executed until a mismatch is found, then the mismatch is analyzed and bugs are fixed. Beside the bugs, I will also briefly report on the obtained execution metrics in the following. Our testing process showed that the RTL core already had a very solid implementation of the RISC-V unprivileged ISA. Only very few special cases have triggered a mismatch with the ISS here. Most bugs were related to the RISC-V privileged ISA, in particular the CSR handling. In total, we found more than 10 bugs in the RTL core, which include CSR access errors with wrong access permissions or incorrect update semantics, or decoder errors where valid instructions have been interpreted as illegal, or errors in trap handling. For example, where the MRET instruction continues at the wrong address for some special instruction sequences that involve multiple MRET and illegal instructions. MRET is a special RISC-V instruction to return from the trap handler and is used in a very regular way by the software, while our approach allows to comprehensively stress test the MRET instructions and others, which can be very important to find intricate bugs. In addition to bugs in the RTL core, we also found a bug in our reference ISS, where incorrect trap-specific information is provided on a very special case. The light-wire test generation process and tight co-simulation between the ISS and RTL core enable our approach to achieve a very high performance. In 1 hour, it processed a total number of 226 million instructions. Processing an instruction involves generating it, executing it on the RTL core and ISS, and comparing the results of both. Breaking it down, we obtain around 63,000 instructions and 229,000 cycles per second. In average, 12 million accesses and more than 700,000 different values have been observed per register. In addition, more than 99% of all possible immediate values have been observed as well in the testing process. Therefore, beside the high performance, our approach also enables a broad coverage. In combination with support for and pipeline levels. For this evaluation, we use the standard configuration. Spinal HDL provides an option to generate a Verilog description. By using the Verilator tool, we obtain a C++ RTL model from the Verilog code. Then we have integrated the C++ RSS of our open source RISC-V virtual prototype in a co-simulation with the RTL model. Two steps that are continuously repeated. The test bench is executed until a mismatch is found, then the mismatch is analyzed and bugs are fixed. Beside the bugs, I will also briefly report on the obtained execution metrics in the following. Our testing process showed that the RTL core already had a very solid implementation of the RISC-V unprivileged ISA. Only very few special cases have triggered a mismatch with the ISS here. Most bugs were related to the RISC-V privileged ISA, in particular the CSR handling. In total, we found more than 10 bugs in the RTL core, which include CSR access errors with wrong access permissions or incorrect update semantics, or decoder errors where valid instructions have been interpreted as illegal, or errors in trap handling. For example, where the MRAT instruction continues at the wrong address for some special instruction sequences that involve multiple MRAT and illegal instructions. MRAT is a special RISC-V instruction to return from the trap handler and is used in a very regular way by the software, while our approach allows to comprehensively stress test the MRAT instructions and others, which can be very important to find intricate bugs. In addition to bugs in the RTL core, we also found a bug in our reference ISS, where incorrect trap-specific information is provided on a very special case. The light-wire test generation process and tight co-simulation between the ISS and RTL core enable our approach to achieve a very high performance. In 1 hour, it processed a total number of 226 million instructions. Processing an instruction involves generating it, executing it on the RTL core and ISS, and comparing the results of both. Breaking it down, we obtain around 63,000 instructions and 229,000 cycles per second. In average, 12 million accesses and more than 700,000 different values have been observed per register. In addition, more than 99% of all possible immediate values have been observed as well in the testing process. Therefore, beside the high performance, our approach also enables a broad coverage. In combination with support for unrestricted instruction sequences to cover highly irregular control flows, our approach is very suitable for extensive stress testing. On this slide, you can see a distribution of the generated instructions. On the x-axis, you can see the difference being considered. On the y-axis, you see the number, how many times this instruction has been generated. In average, every instruction has been generated around 4.5 million times, with a maximum of 6 million and a minimum of 3 million times per instruction. So now I would like to discuss briefly a few directions for future work to further improve our approach. One direction would be to investigate parallelized test sessions using different random seeds and utilizing FPGAs to further boost the testing process. Another direction is to consider testing the interrupt interface of the RTL core, which is quite challenging as it needs to be synchronized with the instruction stream co-simulation to avoid spurious mismatches between ISS and RTL core. Yet another direction is to extend and evaluate our approach on additional RISC-V ISA extensions. As already mentioned, we believe that our approach is very well prepared for this task due to the generic on-the-fly instruction stream generation. Finally, we plan to investigate new coverage metrics that also consider RTL-specific coverage and develop execution feedback mechanisms to further guide the test generation process. So in summary for the second part, we presented an efficient processor verification approach for RISC-V using an endless and dynamically evolving instruction stream generation. The three main benefits include that the instruction streams has no restrictions on the control flow and long test sequences are considered by being endless. And in addition, a high simulation performance is obtained by using a tight co-simulation. We found and fixed several bugs in the industrial pipeline RISC-V core from MinRes, in particular from the TGF series. Finally, you can find our most recent and related RISC-V approaches at systemc-verification.org/RISC-V.
So, hello. So this is Daniel, and also Vladimir and Ike are in the video. So hopefully there are some questions. So do we see some Q&A window, or is it with audio? So in the chat, no, in the chat are no questions yet, or?
Yes, if anyone has a question, they can write it in the chat, or they can raise their hands so I can unmute them so they are able to ask their questions.
Okay, so are there any questions from the audience? If this is not the case, we can, of course, comment some or provide some more details on stuff we have done. Here, please. No. There's not a question yet, right? So, Vladimir, you want to, or Ike, you want to add something?
I guess this is more to Vladimir.
Yes, I can perhaps tell a little bit more about the bugs we have found. I mean, we gave a short overview on the bugs, and our approach has, for example, been very effective. Or one particular strength of the approach is also to find bugs in CSR handling, for example, right? Because in RISC-V, the ISA, it's very, very configurable and very modular designed. And in particular, CSR testing is a very difficult problem, because in implementing CSRs, you have a lot of freedom, basically how you can implement them. And it's the design is very intricate, and it requires, I would say, very strong simulation-based or testing approaches in general to find bugs in CSR behavior. And our approach has been very effective there. For example, finding bugs in trap handling functionality. It involves updating the CSRs, for example, but also having something like side effects of CSR testing. And also, as I mentioned in the video briefly, like the MRET instruction, this was also a very intricate bug, which involved like several instructions and jumps to the trap handler and return instructions for it to occur, and stuff like this. And yeah, I also think that the performance is quite good of the approach, right? So with 200 million instructions per second, it's very effective. So you can really use it for deep testing, but also for very broad testing, right? So by randomizing instructions, you really have the randomized instruction as the foundation, and then you can use it to have a very broad coverage of your testing approach. And of course, this is also something which you want to look in future work, right? How to design good coverage metrics. Basically, right now we are like measuring the number of instructions, and we have the randomization process. We have mutation procedures basically to guide the testing process. But it would also be very nice to have like a functional coverage metrics, for example, to measure the verification quality even further, or even like use feedback curves from the coverage metrics to guide the test generation process further and so on. This would be also very interesting to see. And another interesting direction, I think I also mentioned it a bit in the future work section. This approach it's very good to parallelize, right? So you can like start different verification instances, basically use random seeds, and then you can get even broader coverage, because it's easy to parallelize, right? You can just use a different random seed, and then the test generator will basically go in a different direction, more or less.
Okay, maybe are there any questions? Here, at least some comments. Yeah, hello.
Hi, I muted myself, so I wanted to ask, so you showed something on a slide about coverage. You said that you have 96% coverage of immediate values. So you do collect some kind of coverage currently, but not...
Yes, we do.
Because I wanted to ask exactly this, because on the one hand, you say that you have some coverage, but then it's not advanced enough, the model. That's what you mean.
Yes, exactly. It's very, I would say very rudimentary coverage. So what we did on coverage is basically we counted, let's say, the number of instructions we generated at all. This is like the very basic metric. I wouldn't even say it's coverage, it's metric. Then we have a little bit of coverage, like the number of accesses to registers and the combinations of register accesses, and the number of values, for example, which we write into immediates, and also in the registers. This is what we measured. And in particular, when you think about immediates, then you also have some sort of, let's say, very basic coverage metric, because immediates, they are typically fixed size, right? They're encoded inside of the instruction, and we have different immediates. For example, when you perform an addition with an immediate, then the immediate can have like 12 bits of length, and it's a sign immediate. So it has a value range from minus 2048 to plus 2047. And then we can see like which values have been hit in this immediate range, right? And when you look in all immediates, like the computational immediates, the immediates used for branching, because for branches you encode the relative jumping offset into the immediate, And we have even larger jumps, and we have immediates for memory accesses. This is like, so you take the register value as the base address and use the immediate to access the memory. And when you put them all together, we had like observed 99.6% of all possible immediate values. And I think it was around more than a few millions of different immediates.
But is this like also grouped by instruction? Because I mean, like if you use an immediate in an add, is a different thing than if you use an immediate for a jump, right?
Yes,
It's
this
like,
is true.
so you collect them by.
If I remember correctly, I think yes.
I mean, I guess
it may be. I think if I remember correctly, I think we really I think we combined them, but I wouldn't yeah, promise. Perhaps we also split. I don't remember exactly. I had to look.
No, because I mean, like, I guess the entire idea is that you want the immediates to see that you hit corner cases of the CSRs, right? That you hit overflow.
Exactly. And it was like also getting like a very basic understanding of the coverage, because it was not. We thought a little bit about coverage, but we thought about it using it for future work. Basically, right now we used it really as just a basic metric, just to see that it works more or less. Yeah.
And also, Tudor, I've also put in the chat some general link where we have also the PDFs of our paper available, and also in the context in the first part I presented with respect to this compliance testing. We also had one previous work even where we looked on coverage using also fuzzer flow, and then improving coverage, let's say validating or checking the correctness of the ISS model itself. And there we, for example, integrated specific functional coverage aspects in the LLVM flow that we could increase the coverage at the end. So. But this is also, you found some details in these papers, but of course, feel free if this is not enough to contact us for the details.
And this whole thing, I mean, I came in a bit late. So what do you use? You have some libraries that you use for randomization that you wrote yourself? Is it something?
For this one, we mostly wrote it ourselves, basically. Because the foundation is we can use full randomization pretty much, right? Because with our approach, we have this, we generate one instruction stream for process verification, a single instruction stream, which is endless, and it evolves dynamically at runtime. So the basic idea is really every time the RTL core fetches an instruction, we inject a randomized instruction. And then we collect these instructions and then feed the same instructions into the ISS. And the main difficulty of this approach is really to feed the same instructions into the ISS, because the RTL core and the ISS, they have a different fetch behavior. For example, because the RTL core has a pipeline and it does pre-fetching, but then really throws away the instruction because of a jump, it's taken a different direction, for example. This is like the main challenge involved. It's really been a bit complex to extract the instructions which have been really executed and feed them to the ISS. This was like the main challenge, basically. And as you can see here, the foundation is a full randomization, so it's a pretty simple algorithm, more or less. And then we extended this one, the algorithm, the randomized instructions, to inject valid opcodes, for example. Then you have longer streams of valid instructions, or to mutate instructions to give them some structure. For example, make the destination and source register equal. Or, for example, to inject sequences of instructions, which can be important to load large values into registers, for example, because it requires 2 instructions in RISC-V to load an arbitrary large value into a register. Or, for example, to perform CSR accesses. Because right now in our framework, what we do is we compare basically the register values after execution of a single instruction. We have the ISS and the RTL core, make a co-simulation and compare the register values. To compare CSRs, then we need to load them into registers first. And therefore,
why do you need to load them into registers? Because you don't know when they get updated, or?
Yes, it's a little bit complex to extract them from the RTL core, their value exactly at the exact right time. And so we don't compare the CSR values after each step, but only the normal registers. And therefore, we use the normal instructions to load the CSRs into registers. And these instructions need to be injected into the instruction stream, basically, which we use.
Well, my question was like, I mean, you did the work of synchronizing the RTL and extracting stuff from the RTL to see what it fetches. How easy would this be to port this to a different RTL implementation? I can.
Yes.
I guess this is most of the work, right? I mean, this is the
Yes,
difficult thing.
Exactly. There are two things basically. There's one thing which you said, this extracting the instructions, and the other one is the test generation to make it like as good as possible. Let's say like this. And of course, this instruction stuff, it really depends on the internal architecture of the core. So every time the pipeline changes, we also need to adapt in our approach a little bit. We built an adapter more around the RTL core, so we don't have to update a lot of stuff in our overall test bench design, but only a very specific part, which is extracting the required information from the RTL core. But this part really needs to update every time the RTL core microarchitecture changes, in particular when the pipeline changes and so on. And we observe those changes actually when going from when adding new instruction set extensions to RISC-V. So the RISC-V core, we observed that we need to change this adapter basically. So we started with a basic 32-bit processor with the basic instruction set. So it's just integer instruction set, and then added compressed instructions. And then we observed the fetch behavior changed of the core a bit. And then we also added like multiply instructions, which again had impact. And so we need to adapt it basically every time when the microarchitecture, the pipeline changes. And it happened basically every time when we added a new instruction set extension to RISC-V, to the core using RISC-V. And the change is local, but it's I think, most complex change really. It requires quite some deep understanding of the RTL core behavior, the pipeline basically.
Yeah, but I mean, like this adapter interface, so to say, to the generator, this is something that could be ported to a different core. One would just need to do the work of connecting it to their implementation, to their RTL implementation, to their pipeline scheme and whatever.
Yeah, basically we structured the test bench in a way that the core in this adapter is a unit, and this can be exchanged, and the rest can stay the same. Which means if you get a different microarchitecture implementation, yes, there will be a different adapter, but this is a couple, right? And you always have to have some way to get this abstraction from the pipeline behavior to some instruction accurate representation. Let's put it this way. And this is the challenge we had in the entire thing. But I guess we try. Well, it's a matter of structuring the entire approach so that it gets to some extent portable.
Yeah, like I said, this is, I think, one of the biggest issues, right? Getting it in such a way that you can do it for a different processor as well, because it's nice. You can get some nice results for the one core, but then you want to do it for the second one, and then you see, my stuff was way too tied to the first implementation without even knowing it.
Yeah, that's always the challenge, to get the right grip on that, in the sense that you are not too loose that you lose things, rather not too tight that you are too close to the implementation. Yeah. Right. But I guess we need to finish now. We are already 5 minutes over time, and the next ones are waiting, right? Sorry, Tudor.
Yeah.
No, thank you very much for the.
Sure.
I think we have to close now. Yes.
Yeah.
Okay.
Okay, so enjoy the tutorials and the DVCon, and maybe see you next year.
Hopefully, and then live again. Bye bye.